In this video, I'm going to cover the topics of symmetry and the associated conservation laws that go with those symmetries. And in particular, I'll be talking about the parity, the time, and the rotational symmetries in this video. All right, so since there is no definite momentum, position, or energy in quantum mechanics, then conservation means that either the expectation value is independent of time or the probability of getting a particular result in an experiment is independent of time. So, I mean, these two things are, in I guess the most important ways, kind of saying the same thing. It's saying that the sort of probabilities don't change over time. And so we'll be using this, what's called the Ehrenfest theorem here. This is the generalized version where I just have sort of a general observable there in this derivative here. And so we're saying that, I mean, this part here is essentially saying that if it commutes with the Hamiltonian, then this will go to zero. And this is saying that if it doesn't have an explicit dependence on time, then that will go to zero. And so if it commutes with the Hamiltonian and doesn't have an explicit dependence on time, then it goes to zero. And so that is sort of what we will be looking for here. All right, so if we have some operator q hat here, and we act it on some function here, and we get an eigenvalue multiplied by that function, then we want to know the probability of getting this this qn here. And so this just could be, sort of any kind of thing that you could observe. And so, like with the Hamiltonian, it's energy, but here we're just being very general, and I'll get into more specific examples here in a little bit. So we want to know the probability of that q sub n, and it's equal to the inner product of our function here with the wave function squared, and so the Born rule. So with the evolution of the wave function, so when we want to make it dependent on time, we have it set equal to this. So we have our function here, but now we have this time-dependent part here. And so the eigenstate is an eigenstate of the Hamiltonian here, and this means that the probability of seeing the q sub n is equal to this right here, so all of this squared. So that is the Born rule there. And since we're saying that the Hamiltonian and this q operator commute, they have a complete set of simultaneous eigenstates, and so this function here is equal to the wave function, and so we can put that in here. And so then we see that when we square this complex exponential here, what we're essentially doing is multiplying by the complex conjugate, which gives us 1, and we have that that this is equal to 1 if n equals m, but it equals 0 otherwise because they are orthogonal. And so the probability of seeing q sub n is just equal to this coefficient here squared. And so that means that because we have like c sub n equals c sub n when these are equal to 1. And so the probability of seeing the q sub n is equal to this squared, which is independent of time. And so that's why we would get 0 for the Ehrenfest theorem here. All right, so we can look at one of our symmetries here called parity. And so this has to do with inversion symmetry. And so parity is, so if you have, something that has some shape sticking off on this side, then if it has the same shape sticking off on this side, you could say it's parity, because if you sort of invert both of these into each other, then you just get the same thing back again. And so a 1D parity operator, which is denoted by this uppercase pi here, makes a spatial inversion. And so when we acted on our wave function here. It gives us the wave function with the inputs sort of reversed, and so that gives us this psi prime right here. So the parity operator is its own inverse, because we can see that if we say inverted this thing here and then you inverted it again, you would just get right back to exactly where you were. And so these parity operators are their own inverse, and it's also Hermitian, and so it's equal to its own transpose, its conjugate transpose. So the position and momentum are odd under parity. So we have our position operator here and our momentum operator right here. And what negative parity or odd under parity means is essentially, so if you have a function, say you're in like an infinite square well, and you have a function that looks like this, we see that if we inverted this, we would get something that looks like this instead. And pretend that my drawing is not terrible, but so we have positive here and negative here, then we have positive here and negative here, and so when we do a parity operation on it, we sort of switch those positives and negatives. But we see that if we did the Born rule and squared these things, that we would end up with something, that looks like this essentially. So it would be symmetry after you squared it, but before you apply Born's rule, these have a negative part and a positive part. And this actually shows up in quantum mechanics, because if we have like a p orbital, so we have a p orbital that would look something like this. Well, this side would be positive and this side would be negative, but you can do like a rotation or you can do an inversion on it, and you'll get a lobe overlapping with a lobe. It's just that one is positive and one is negative, and that's just what odd parity is. That's how odd parity works, that you sort of switch the sign on things after you perform the symmetry operation. And a system has inversion symmetry if the parity operator commutes with the Hamiltonian. So if we have the Hamiltonian and our parity operator commuting equals 0, which means that if we do this similarity transformation, we end up with this h bar here, which is just equal to or h prime, which is just equal to the Hamiltonian. And so the Hamiltonian and then the parity operator is equal to the parity operator times the Hamiltonian. So inversion symmetry of a potential means that if it is an even function, so defined as the function with everything negative is also equal to positive, which makes sense if we look up here at this. So if we have our origin right there, then everything in the x is just a mirror image of everything in the minus x. And so that's what an even function is one where the f of minus x is just equal to the f of x. So when we have an inversion symmetry in our potential, that means that our potential term here with the minus input is equal to the potential term with the positive input. So we have that the eigenstates, which are shared with the Hamiltonians in the commute, have an eigenvalue of plus or minus 1. And so if it has a minus 1, then the parity inversion is an odd function. If it's positive 1, then it is an even function. And since we know that these commute, then we have our Ehrenfest theorem here. And so these commute, so this goes to 0, and the parity isn't explicitly dependent on time, so that will go to 0, and so this whole thing will go to 0, which means that an even wave function remains even and an odd wave function remains odd. So parity is conserved in a symmetric potential. All right, so if we talk about parity in 3 dimensions, then the operator does essentially the following, where we take this 3-dimensional vector here and essentially just flip everything into negatives. Or more simply, if we just kind of group all these Cartesian coordinates into r, it just makes us go from the positive r to the negative r. So for a particle in a central potential, such as an atom, the potential has parity, has this even functional parity, which is true of any central potential. Since the eigenstates of our parity operator are simultaneous with the eigenstates of the Hamiltonian, and so the states which are given by this, so we have the radial part of the equation and the spherical harmonics. These are eigenstates of parity, which looks like this. We have this -1 with the L there. When L equals 0, that's when we have our s orbital. And so an s orbital is just a sphere, and so that is obviously going to have positive symmetry. So L being 0 will make this just go to +1. But when L equals 1, then we have a -1 there, and that's when we have the p orbitals, which, as I said, do in fact have the negative symmetry or the odd symmetry. Then if L is 2, this becomes even again, and that makes sense because then we have our d orbitals, which look more like this. So I don't know why I chose to do those in dotted lines, but we have positive, positive, negative, negative. And so you see, if we do an inversion sort of through the center here, these two positives will just sort of exchange with each other, and these two negatives will exchange with each other. And so that's why, that just sort of makes intuitive sense that this is sort of what we're doing when we apply the parity operator to our wave function here. All right, so now we can look at time symmetry here. So the time-dependent Schrodinger equation is this, and the time evolution operator has our wave function here, so it's a function of position, and we're at time 0, sends it to some other time t into the future. If the Hamiltonian is not a function of time, then we have this here, this sort of Taylor expansion for our wave function here. So then we can make these sort of substitutions here, and we end up with this, which we can then say that because all of this here is the definition, or is the Taylor expansion of the exponential, that we just get this exponential here times our wave function. And so the time operator is just this exponential here with the I over h bar and then the Hamiltonian in the exponent there. So if the Hamiltonian is hypothetically a function of time, then the wave function here at time t has to be equal to the time evolution operator here, which is a function of what time it is now and when it started. And this, the wave function, is a function of when it actually started. So when we sort of acted the time evolution operator on it. And an infinitesimal then would be, so if we have the time evolution operator going from so if our t here is just equal to our t sub naught plus, something really small, some really tiny amount of time, then we can expand it out this way and ignoring higher order terms. So we get this 1 minus I over h bar, then the Hamiltonian, which is a function of the time that it began. But time translation invariance means that the time evolution is independent of when it happens. And so the t sub 0 shouldn't matter, because if you start your experiment now, that shouldn't give you something different than if you started it 10 minutes from now, or if you started it 5 years ago, or if you started 100 years into the future. And so it's independent of when it happens. So if we have this time evolution operator here starting at t1 and going to t1 plus delta is going to be exactly the same as if we started at some other time and then went to, just delta ahead of that time, regardless of when you started. And so this means that this right here, so the H or the Hamiltonian starting at T1 is just equal to the Hamiltonian starting at T2. And so the Hamiltonian is necessarily time independent. So we have this explicit time dependence being 0. And I guess you could obviously say that the Hamiltonian is going to commute with itself, and so that Ehrenfest theorem is going to be 0. This means that that energy conservation is a result of time translation invariance. Because remember, the Hamiltonian is telling us the energy of something. And so the energy conservation is a result of this time translation invariance. So then we can think about the rotation here. So the operator that rotates us around the z-axis. So we have this operator here, and we rotate around the z-axis, which is this phi variable here. It gives us this phi minus, this other sort of fancy phi, I guess. So it just gives us, some change in that angle when we rotate around the z-axis, which is related to the z component of angular momentum. And so just like we gave the Taylor series for the spatial translation operator, which was related to momentum, and I did that actually in a previous video, but we also did this above for the time translation operator. We did the Taylor expansion, which was related to the Hamiltonian. The same relation between the rotation and the z component of angular momentum gives this Taylor expansion here. So we just do this Taylor expansion here. We can sort of collect all this stuff into here, which is the Taylor expansion of the exponential, and so we get the exponential here with our LZ operator in it. And so we do an infinitesimal rotation delta, dropping the higher order terms. We get this. And so then the position operator, this x hat here, transforms. So we are doing a sort of similarity transformation here with our rotations. So we just put this and this on either side. So these are the complex conjugates of each other. And so we get this x hat plus the I delta 8 over h bar, and then the commutation of LZ and the x hat. And since we already know from earlier that these don't commute with each other, so we get this I h bar y hat, then the x plus I delta over h bar I h bar y, so that just gives us this right here, the x hat minus delta y hat there. And similarly for the y hat prime here is just the y hat plus delta x hat, and then the z prime is just equal to the z, which gives us the following matrix. So we see we have these two off diagonal elements here. And so when we do the transformation, we make the x and y both become dependent on each other. This works since in an infinitesimal rotation, the infinitesimal angle, so this phi here, goes to 0 because we're saying it's infinitesimal. In the infinitesimal translation delta greater than 0, we have that the cosine will go to 1 as this goes to 0. And as this gets arbitrarily close to 0, this just becomes our delta here, so our very, very small amount. And so we actually just get our rotation matrix right here. So we have the cosine, the minus sign, the sine, and the cosine here, which is just the same as what we had for our deltas here. And so we can think about this in 3 dimensions. We do a rotation in 3 dimensions that From above, we already know that is our exponential here. We have this n, which is just sort of telling us which direction we are doing this rotation in. So in a central potential, like an atomic nucleus, the potential is rotationally invariant. As such, a rotation in any direction commutes with the Hamiltonian. So we have that our rotation in any direction commutes with the Hamiltonian. And since for an infinitesimal rotation, so we have this dropping the higher order terms, means that our L here commutes with the Hamiltonian, and so L doesn't change in time. So once again, we know that this commutes with the Hamiltonian, so that goes to 0. We know that this doesn't have any explicit dependence on time, and so that goes to 0. And so the H hat, the LZ, and the L squared have a complete set of simultaneous eigenstates. And so we have this as our Hamiltonian acting on the wave function, then our LZ angular momentum, then our L squared angular momentum. And so we see where we get the energy, we get the M, and we get our L's here. And we can know all three of those things at the same time because those are simultaneous eigenstates. And that's where we get our quantum numbers, the N, the L, and the M from, is knowing these three things. But anyway, that is everything I wanted to talk about in this video about the symmetry and conservation laws. So I hope you found this video helpful, and I will see you in the next one.